Hello, and welcome to this e-seminar, which will provide an introduction to the optimisation of quantitative real-time PCR assays. It is assumed that you have a working knowledge of quantitative PCR and have viewed the previous e-seminar on PCR assay design. For those who may benefit from additional information, please refer to the LGC publication, Good Practice Guide for the Application of Quantitative PCR, which is free to download from the LGC website at www.lgcgroup.com/NML. The development of fluorogenic PCR applications has enabled the monitoring of PCR product accumulation in real time, and has been widely adopted for the detection and quantification of a broad range of nucleic acid sequences. Many real-time PCR assays that have been developed are non-commercial, in-house designs for which the optimal reaction conditions have not been determined. Guidelines for the verification and optimization of real-time PCR assays are available, but are frequently highly technical and complex in content. This e-seminar will provide you with a basic introduction to the fundamentals of assay verification and optimization, and provide guidance and best practice on how to undertake the process. The key stages in real-time PCR assay development are summarised in the flow diagram presented on the slide, and are described in detail in the e-seminar, An Introduction to Designing Quantitative Real-Time PCR Assays. This e-seminar will describe the steps which comprise stage 4 of the process, and will therefore focus on assay optimization and performance characterisation. The design of conventional real-time PCR assays has been described in detail in the e-seminar An Introduction to Designing Quantitative Real-Time PCR Assays. The process is relatively straightforward, provided the guidelines presented on the slide are followed. Primers should be 20 to 24 bases in length, with a melting temperature, Tm, of approximately 60 degrees centigrade. For hydrolysis probe assays, for example TACMAN, probes should be 20 to 30 bases in length, with a melting temperature 7 to 10 degrees higher than the average for the primer pair. Target regions of high GC, repetitive and palindromic sequences should be avoided. Finally, primers, probes and amplicons should lack significant secondary structure or regions of self-complementarity. Most real-time PCR assays designed to the criteria outlined on the previous slide will perform adequately. However, all assays have specific conditions under which they will perform optimally. Factors which influence assay performance include buffer conditions, the concentrations of primers and probe, the primer annealing temperature, the magnesium concentration, and even thermal cycling conditions. Optimization of some or all of these factors is required to ensure adequate assay sensitivity and specificity. In the following section, we will provide guidance and best practice for the stepwise optimization of real-time PCR assays. All real-time PCR assays have specific requirements for optimal performance. Factors which influence performance include template quality, the reagents employed, and the thermal cycling instrument employed. Assay optimization is performed in a stepwise manner. The primary focus of the procedure is on manipulation of primer binding kinetics. This can be influenced by changing the concentration of the primers and changing the primer annealing temperature. A number of additional parameters may be modified in order to optimize the performance of an assay. These include varying the magnesium concentration, optimizing the concentrations of the PCR reaction components, primarily the concentration of deoxynucleotides and Taq polymerase, and modifying the assay thermal cycling parameters. A magnesium concentration of between 1.5 and 2.0 millimolar is optimal for Taq DNA polymerase activity. However, the optimal concentration will depend on the concentration of template DNA, reaction buffer, and deoxynucleotides, each of which has the potential to chelate magnesium ions. As a rough guide, the optimal concentration should be determined by supplementing the magnesium concentration in 0.5 millimolar increments up to 4 millimolar. A concentration of 200 micromolar is typically employed for each deoxynucleotide. However, this can be substituted for a concentration of between 50 to 100 micromolar, where assay fidelity is required rather than yield of PCR product. Taq DNA polymerase is normally used at a concentration of between 0.5 to 2.0 units per 50 microliter reaction volume. As a rough guide for optimization purposes, the optimal concentration is normally in the region of 1.25 units per 50 microliter reaction volume. The majority of qPCR assays designed to the criteria specified previously will function adequately under standard 3-step thermal cycling conditions. Aside from the normal heat activation step required by commercial hot start Taq DNA polymerases and the empirically determined primer annealing temperature, the denaturation temperature and its duration, the duration of the annealing step, and the extension time can be modified to improve assay performance if required. For effective denaturation during thermal cycling, 15 to 30 seconds at 95 degrees centigrade is normally sufficient. Similarly, 15 to 30 seconds at the optimal annealing temperature will be sufficient. Extensions are normally performed at 68 degrees centigrade. As a guide, extension times of 1 minute per kilobase of target should be employed. For products of less than 1 kilobase, an extension time of 45 to 60 seconds is normally sufficient. The first step in assay optimization is verification of primer and probe design. Verification of the design ensures that the oligonucleotides are homologous to the target sequence, do not adopt significant secondary structure, do not hybridize with one another, and that the reverse complement primer sequence is correctly orientated. A number of software tools are freely available to perform the verification process. These include Primer Blast, which can be accessed at the NCBI website, and OligoArchitect, which is available online at the Sigma Aldrich website. An example of assay verification using Primer Blast is shown on the slide. This application may be used to design and verify real-time PCR assay designs. To validate an assay design, the DNA sequence for the target is pasted into the sequence dialog box, or alternatively, a sequence accession number may be entered. Forward and reverse primer sequences are then entered into the respective input dialog boxes, and the application run normally using the software defaults. An example of Primer Blast output is presented on the following slide. The typical output for a primer design using Primer Blast is shown on the slide. The output is described in detail in the e-seminar, An Introduction to Designing Quantitative Real-Time PCR Assays. However, in this instance, your attention is directed to the highlighted text boxes. Box 1 indicates the location of the primers in the target sequence. Box 2 lists the sequence characteristics of each primer. Box 3 gives an indication of the likelihood that primers will form secondary structures. Box 4 provides an indication of the likelihood that primers will form primer dimers. Following design verification, the next step is to determine the optimal primer annealing temperature. If the temperature is too low, the amplification can result in non-specific PCR products being generated. If it is too high, the PCR yield may be compromised. As a rough guide, the optimal primer annealing temperature should be approximately 5 degrees below the melting temperature of the least stable primer. Alternatively, a theoretical annealing temperature can be determined by applying the formula shown on the slide. This states that the annealing temperature is equivalent to the sum of 0.3 times the melting temperature of the primer plus 0.7 times the melting temperature of the PCR product minus 14.9. However, in practice, it is frequently necessary to determine the annealing temperature empirically. Primer hybridization is primarily influenced by the concentration and melting temperature of the primers. However, the kinetics of primer hybridization are also influenced by a number of addition factors, including composition of the PCR reaction buffer and the presence of co-solvents. Therefore, it is recommended that optimal primer annealing temperatures be determined empirically. This procedure can be undertaken by employing a fixed primer concentration while varying the annealing temperature. Most hydrolysis probe assays will work using a final primer concentration of 900 nanomolar and which can be employed while varying the annealing temperature. As a rough guide, the annealing temperature is generally 5 degrees centigrade below the melting temperature of the least stable primer, and can be used as a guide for the range of temperature to evaluate. The optimal annealing temperature will be that which results in the earliest quantification cycle and greatest normalised fluorescent reporter signal, i.e. the highest delta Rn. The conventional approach for determining the optimal primer annealing temperature involves maintaining the primer concentration while varying the annealing temperature. In practice, a temperature range of 1 degree centigrade to 8 degrees centigrade below that of the primer with the lower melting temperature at intervals of 1 degree centigrade will be sufficient. Once an optimal annealing temperature has been identified, the absence of secondary PCR products should be confirmed using gel or capillary electrophoresis or by employing a DNA melt curve approach. Once the annealing temperature has been determined, step 3 involves varying the primer concentrations in order to identify the optimal value. This may be performed by using a primer concentration matrix, such as that shown on the slide. The optimal primer concentration combination is the one that results in the lowest quantification cycle value and highest normalised reporter fluorescence signal, i.e. the highest delta Rn. In some instances, this will require the concentration of the primers to be different. An example of the results from a primer concentration optimization is shown on this slide. In this example, the optimal final concentrations are different. For the forward and reverse primers, the optimal concentrations were determined to be 900 and 300 nanomolar respectively. Many probe-based real-time assays will perform adequately using a final probe concentration of 250 nanomolar. However, to achieve maximum sensitivity, titration of the probe should be undertaken to identify the optimal concentration to employ. This is normally performed while employing the optimal primer concentrations and lowest concentration of the target DNA likely to be present in the test sample. Optimal probe concentration is that which enables the most sensitive but reproducible detection to be achieved. Where maximum sensitivity is not required, a lower concentration of probes may be used to reduce costs. In the following section, we will provide an introduction to the evaluation of real-time PCR assay performance and provide guidance and best practice on how to proceed with the determination of a series of key performance indicators. Following optimization, a number of key performance indicators should be evaluated. These may include assay specificity, PCR efficiency, data linearity, dynamic range, limit of detection, and limit of quantitation. Assay specificity may be determined by examining the PCR product using either DNA melt curve analysis or gel or capillary electrophoresis. Assay performance is conventionally determined using a standard curve-based analysis, which involves generating a serial dilution of a reference material over a sufficient range of concentrations to encompass the dynamic range of an assay. In addition, a minimum of triplicate PCR replicates at each concentration is recommended, with the analysis being performed on multiple occasions. Standard curve analysis enables the PCR efficiency to be determined as well as the dynamic range and precision of the assay. Assay specificity may be determined through examination of the PCR products generated. This may be performed using either DNA melt curve analysis or gel or capillary electrophoresis. With DNA melt curve analysis, the presence of more than one melt peak is indicative of the presence of multiple PCR products, including primer dimers, as is illustrated here. With electrophoretic analytical approaches, the presence of multiple PCR products is confirmed by the detection of more than one band, as illustrated. Assay performance is normally determined through standard curve-based analysis. These curves are frequently generated through a 1 in 10 serial dilution of a reference material. The dilution series should span a wide concentration range in order to encompass the expected dynamic range. As a rough guide, a concentration range spanning 11 logs will be sufficient. Each dilution should be analysed in triplicate and the analytical procedure repeated on multiple occasions in order to generate a robust dataset. In practice, a graphical plot of CQ against the log of target concentration should be generated and the line of linear best fit determined. The standard deviation for the line of best fit for the data is an indication of the linearity of the data. PCR efficiency can be calculated from the gradient of the line of best fit to the standard curve data using the equation shown on the slide. The list presented on the slide summarises the critical values for the assay key performance indicators described on the previous slides. Critical criteria include that the gradient of the standard curve should be between -3.6 and 3.1, and that the PCR efficiency should be between 0.9 and 1.1. In addition to these performance indicators, the coefficient of correlation R² for the data employed to generate the standard curve should fall between 0.98 and 1.0, and the quantification cycle values for PCR replicates should be similar. Finally, the template concentrations used to generate the standard curve should encompass the range of expected target concentrations in the test samples. Prior to adoption of an assay for analytical purposes, a full validation of the method is required. The parameters considered for this purpose include the key aspects of assay performance, as well as assay specificity and assay sensitivity, including the limits of detection and quantitation. Although evaluation of these parameters is necessary to comply with the full method evaluation, it is beyond the remit of the current e-seminar. The listener is referred to the Eurochem Method Validation Guide and European Network of GMO Laboratory Guidelines. In the following section, we will provide a summary of the points covered in this e-seminar. To summarise the main points covered in this e-seminar, assay design should always be verified prior to optimisation or adoption. Optimisation is routinely performed for assay annealing temperature and for primer and probe concentration. Additional optimisation may be undertaken for magnesium concentration, assay reaction components and thermal cycling strategy and conditions. As a rough guide, the annealing temperature is normally approximately 5 degrees centigrade below the melting temperature of the primer, with the lowest melting temperature. The theoretical annealing temperature may be calculated using the equation on slide 12. However, the parameter frequently requires empirical determination. Optimal primer concentration may be determined through the use of a concentration matrix. An example matrix is presented on slide 15. The optimal primer concentration will generate the earliest reproducible quantification cycle. However, this may require the use of different forward and reverse primer concentrations. Assay performance should be evaluated for both specificity and sensitivity, as well as PCR efficiency and linearity of the data generated. Specificity can be determined through the use of gel or capillary electrophoresis, or through the use of DNA melt curve analysis. Assay performance, including determination of dynamic range and PCR efficiency, can be performed through the analysis of a standard curve generated from the serial dilution of a reference material. We would like to acknowledge the support received in preparing, delivering and funding this e-seminar, in particular the Department for Environment, Food and Rural Affairs, the Government Chemist Programme for 2017 to 2020, the Department for Business, Energy and Industrial Strategy, the Food Standards Agency and Food Standards Scotland. And finally, we would like to thank you for your attention.